Now, with the theory out of the way, we can actually use these elastic forces and energies to solve a variety of problems. At the end of the day, this is actually not going to change too much how we go about solving the problems conceptually. The only difference is we're now going to have additional forces here. So here's a particularly relevant example. Let's say you take a 10 kilogram mass and you suspend it vertically from a spring. And you find that this particular spring, once you hang the mass up, gets stretched 15 centimeters downwards, or it undergoes a displacement of negative 0.5 or 0.15 meters in the y direction. And you're told that after it stretches there, uh, it comes to a complete stop. In other words, it is stationary once it has stretched this particular amount. At the end of the day, we're assuming this happens on Earth. So because it's been displaced uh, downwards from its equilibrium position, it will experience a force that results from the acceleration due to gravity. And what you've been tasked to find is the spring constant, K, of this particular spring-like system. All right. So because we're dealing with the spring constant K here and everything is stationary, this is one of the places where you can use forces to very quickly solve this problem. As always, what I'd like you to do anytime you see a force problem is please read the problem very carefully and see if you can determine the net force of this particular hanging mass that we need to examine. Give yourself a couple minutes, please pause the video, and we'll start back up in a few. Now, to find the net force, one of the key words here is the fact that it is stationary. The minute you see the word stationary, what you can always find or intuit is that the net force must equal to 0, right? And this is the vector net force, so we're going to bold that. All right, so that's always where you should start. So there are going to be more than one forces here, or more than one force here. We need to ensure that they add to 0. The next thing that you're going to want to do is figure out how many forces are going to be present here. So again, pause the video, give yourself a little bit of time, see if you can determine how many forces are present here and where these forces are going to come from. Sorry, I spoiled how many forces are present here. So if you've done this, there will be 2 forces present here. These 2 forces come from 2 different places. One of the forces is actually going to pull down on the mass, and this particular force is actually going to come from gravity. Because we are on Earth's surface here, gravity is going to pull down on us no matter what we're doing. So there's going to be one downward force, like so. The second force actually comes from the fact that our spring is stretching. This is this elastic force that we just talked about. Now, the elastic force is always going to be in the opposite direction of the displacement of the spring. So because the displacement of our spring is downwards here, our elastic force, or the force from our spring, is going to be in the opposite direction to that displacement. So our spring force here is going to be opposite to that displacement from equilibrium. Now, the next thing you're going to want to do is you're going to want to see if you can figure out what these forces are. Now, for the spring force, we're actually going to find it indirectly due to the fact that we know our net force has to be equal to 0. For the gravitational force, though, we can actually find that here because we have the mass and we have the acceleration due to gravity. So what we're going to do down here is we're going to find the force of gravity. The force of gravity can always be found by taking the mass of your object and multiplying it by the acceleration due to gravity. And the mass here is a scalar, so we're going to take the bold off of it. Now, here we know that the mass is 10, and I know that the acceleration due to gravity is 0 in the x and negative 9.8 meters per second in the y. Again, we'll leave off the units because everything here is in fundamental SI units. Now, what you can do here is you can simply multiply these two things together, And what you will get is you will get a force that is 0 in the x and negative 98 newtons in the y. Now, the next step from this is to actually go back up here to our net force equation. We know that we have a net force here, and this net force must always be equal to the sum of our individual forces. So here I have two forces. I have the force of gravity, and I have the force of the spring. I need to make sure that together these two individual forces add up to the net force. And I know that the net force has to be 0. This allows me to very quickly solve for the force of the spring. Right, so we're going to use the force of gravity that we know, and we're going to solve for the force of the spring. So again, do a quick pause of this video here. Make sure that you can find the force of the spring. If you've done this correctly, the force of your spring needs to counteract gravity in order for them to add up to 0. Therefore, the force of your spring must be positive 98 newtons in the y. This is the only way that you can have these things add to 0. Now, once we have this force of the spring defined, it's actually rather straightforward to find our spring constant K. Because at the end of the day, this force of the spring, since we are dealing with ideal one-dimensional springs, must equal to negative the spring constant K times the displacement from equilibrium. Right? So this has to be true. K is always just going to give us a positive scalar quantity, which is why I'm not bolding them. If you plug in what we have here, I know that the force of the spring is 0 and 98 newtons in the y. And this must be equal to negative K times 0, 0.15 meters in the y. So this is the equation that I need to use in order to get to K. This one down here at the bottom. Now, as always, you can split any vector equation up into x parts and y parts. So the x parts here, you'll have 0 is equal to k times 0, which is not particularly helpful. It doesn't really matter. You won't get anything useful out of that. But if you take a look at the y parts here, we'll have 98 is equal to negative k times 0.15. So we can use the y parts here to get us an equation that we can solve, where we get 98 is equal to negative k times 0, comma, negative 0.15. Do me a favor, add the negative sign in up here at the top. I forgot to put it in. All right. So putting these together, you can rearrange this. 1 second here. We're just going to start this over because I screwed this up. Get rid of u. We'll rewrite this here. 98 is equal to negative k times negative 0.15. There we go. And you can rearrange this and solve this. The two negative signs will cancel out. And this gives you a nice single variable equation that you can solve for. So if you divide these out, you will get 653. And as for the units, it'll just be in newtons per meter, because our force was in newtons and our displacement here is in meters. All right, so with that, you basically found the spring constant K.